Okay, hello everyone, and welcome to today's edition of our Extreme and Probabilistic Combinatorics webinar. Before we start, let me go through the usual technical remarks. This webinar is being recorded, and we will post it on YouTube eventually. If you have any question, I hope our speaker is fine if you just, go ahead and ask it at any moment. If you have a problem with your audio, then you can also type it in the chat. And if the speaker doesn't notice, then I will read it out for him. And so now it's my pleasure to welcome Jozsef Solymosi from University of British Columbia, and Jozsef will talk about the Erdős unit distance problem. So Jozsef, please.
Thank you very much. Yes, please ask any questions or anything. Sometimes my internet is not as good as it's supposed to be. So anyways, let me know if there are any questions or things to specify. Okay, so I'm going to talk about Erdős unit distances problem. This is a problem from 49, I think. At least that's when it was published. Probably it comes from an earlier date, but this is one of the great questions of Erdős, in particular in discrete geometry. But what I'm going to talk about here includes, of course, discrete geometry, but also tools from graph theory, graphs from the theory of hypergraphs, and tools from algebra, even a bit of number theory, time to time. Right. I won't solve the problem and I won't improve the presently known best bound. I have to declare it at the very beginning. On the other hand, I will show you some directions which are promising and might lead to some improvements. Also, I'm trying to show why is it so hard to make any progress here. You know the other, I will define the problem in a minute, but many of you know the other problem, the Erdős distinct distances problem, which had gradual improvements up to the point when Larry Guth and Netz Katz almost completely proved it, that the distinct distances among endpoints on the plane is always at least n over log n. Well, the conjecture is n over square root of log n, but this is almost sharp. So this is from 1949. And again, what is the question? The question is that, or the conjecture, let me state it as a conjecture, among endpoints in the plane, at most n to the 1 plus epsilon, so almost linear, but a little more than linear, pairs are at distance 1. So here is the name of unit distances. Of course, you can choose any distance here. Scaling will move it to 1. And let me jump immediately to one proof. And it's very easy to see that, what did I say? Yeah. That n to the 3/2, it was observed by Erdős. It's an immediate observation. Is an upper bound. So I'm going to use the notation UN. This is the number, or the maximum number of unit distances among endpoints, and we are in the plane, so it's R2 where we are at this moment. And the proof is very simple. If you have a cherry, 2 points, distance 1, then maybe you have one more, but there is no way to have one more. So out of any pair, you don't have more than one. So if you do the counting and the calculation, it's just basic graph theory, then you have n to the 3/2. I can jump immediately, but that's another jump, for the currently best known bound. So the best known bound, as many of you know, is n to the 4/3 in magnitude. And it's a relatively old problem of Spencer, Samarady, and Trotter. So they proved it, and now it has various proofs, the theorem, but maybe the most proof comes from the crossing number, which we will see. So this is a very combinatorial proof. And so this proof and all the following proofs are combinatorial proofs. Why is it important? Because as we will see, if we are just using plain combinatorics, then this bound is, in a certain sense, is tight. You have to go beyond that. You have to, in order, if the conjecture is true, or if you want to break the n to the 4/3 bound, then you really have to use that we are talking about the unit distance as the L2 norm. Because there are many other norms where the unit distance in those norms are really n to the 4/3. I will show you a few examples, but before that, I still owe you an explanation. Why do we have here n to the 1 plus epsilon? Why don't we conjecture that it's linear in n? Well, it's also from Erdős paper, so let me just mention, if you take the root n by root n, about root n by root n integer lattice, and the n points there, then here in this construction, un is, well, it's larger than n to the 1 plus, don't have much space, but a little thingy, this is c over log n. Anyways, something small. It comes from number theory. So if you see that, how many ways can you solve the equation a equals x squared plus y squared, you know that for a certain number a, you can, if you check its prime factorization, then you get exactly how many. It depends on the divisors on of form of prime divisors of 4k plus 1, and for some numbers this is pretty large, and that's why you scale down this root n by root n integer grid, that this popular a will be the unit. Good. So this is a little bit of number theory already, but let's see. So let's see the claim that I have my notes, the hardness of breaking. N to the 4/3, so the 4/3 bound. Now, the structure comes from Jarnik. Yes, so this is a talk in Prague, so probably somewhere maybe this is correct, or
No, it's not, but it doesn't matter. There is a long accent on I, so this Hungarian dash.
Here?
Well, yes.
Sorry about that. Well, there will be other Czech names later on, so I have to be good. So thank you. It comes, and this is a very interesting construction for various reasons. Again, let's aim for the n by n grid. What I'm going to do now, I'm going to define, or what Jarnik did. You can define a nice convex centrally symmetric curve, and if this is your unit distance, then you will see that it actually the number of unit distances is n to the third. So what we did is that let's choose a smaller integer grid, and here let's see all the vectors which point to AB pairs which are relatively primes. And then you know that if it's k by k, then you have about k squared, well, constant times k squared, and there is also pi involved, but let's not worry. So about k squared such vectors, and using those vectors, you can build this convex curve here. And if you optimize it, then here you have, if we have n, then n to the 2/3 points. I omit the constant multipliers here. So this is Jarnik's curve. And as n grows, then this will be always a different curve, but this is always well defined. And what you can do is that you can simply extend it, say 4 times the grid. Now it's 2n by 2n. Okay. And this is your center, and those are your unit distances, yes, using this norm. And for any translate, you have many unit distances. So n to the 2/3, that's the degree typically of 1 point, at least if the point is in the center, but you don't need that. Even in the corner, you have at least 1/4 of those distances. So we have about n squared, well, 4 times n squared, times some constant times n to the 2/3 unit distances. And if you set n equals n squared, then this is exactly n to the 4/3 unit distances. Yeah, you can say that here we changed the curve. So depending on n, depending on our construction, we had different curves. And we know that for the unit circle problem, this is just one circle which is given. So this won't happen. But then we can check Pavel's construction. I hope Pavel is here, and I hope that at one point he's going to publish this result. Okay, anyways, sorry, Pavel. I have to bug you with this. Right, so if you see, again, an integer grid, but it's asymmetric. Now here we will have, say, the numbers I over n, where I goes, from 1 to, say, -1, minus n, and here you have j over n squared. So this is much larger. Altogether, you have about n cubed points here. And your unit circle now will be one given curve, which is just, it comes from the y equals x squared, say up to 1. So this is not very symmetric, but you can imagine that this is the same flipped over. And you can check that here also you have n to the 4/3. And now this is smooth and nice. Okay, it's not really smooth here, but if you wish, then you can make it smooth. It won't change anything. And it's a quadratic curve. It's not that far from a circle anymore. So you see combinatorial proofs like crossing number, which is the the main tool here, it won't help. Now I'm just checking that. So Yarnik's result here is the best you can hope for. I wonder how can. So I don't see my headings. Sorry, it's yeah. Anyways. So what I'm saying is that you can't have more than n to the 4/3 points in convex position on an n by n integer grid. This itself is not trivial. There were kind of complicated proofs, but there is a simple proof which is closer to our discrete geometry approach. You can simply use the crossing number. If you remember, I definitely want to record it at least, that if you have any realization drawing of a graph, so if you have a graph, a geometric graph, oops, it doesn't matter, it's geometric graph, and it has much more edges, at least that many edges than the number of vertices. So it's an n vertex graph with e edges. The number of crossings of this graph, the intersections, no matter how you draw it or how you embed it to the plane, is larger or equal than some constant times a cubed over n squared. So this has a very nice proof by Seikei, a probabilistic proof, but this crossing lemma itself comes from Semeridi. Let me see I threw away my notes. I just don't want to. There are similar set of authors for various things. Ajtai, Chvata, Newborn, and Semeridi, and independently by Layton, but this is a very nice tool. I think most of you know it, maybe all of you know it, but how to use it here? Well, you just have this graph where you connect the neighbors. You connect the neighbors as an edge. And one copy, one circle here has n to the 2/3 edges. And then you see all the translates of it. So you know that the number of edges in this graph is at least n squared times n to the 2/3. And among two translates, you don't have more than two intersections. You do the calculation and you have n to the 4/3. The original proofs were analytic and quite complicated, but using crossing number, you can prove such statements. Now, I mention a problem because I promised that I will talk about open problems here, which you might find interesting. If you are into problems in number theory, then this is still an open question, that if you have an n by n grid, integer grid, this is a little bit of number theory, and you have how to state it, and you want to find a curve. So here is a curve, it's predefined somehow. This is a curve C, and you know that this curve is smooth, so it's differentiable, and even the third derivative is, so it's nicely smooth, is larger than 0. And then what you do is that you begin with an n by n grid, that's fine, but then you refine it. So you actually intersect this one with some 1 over, I don't know, k times this grid. Not even this, but you can increase. So what you can do that here, you can say that the whole integer grid, right? You scale down and you see for every k how many points you have on the curve. So the difference here and Yarnik's example is that here you have one given curve. And the difference here and Pavel's construction is that this is really an n by n grid. And this makes a huge difference because there is a very nice result of, it goes into number theory, Swinerton and Daya. It was improved even, well, with some relevance, it was improved by Wolfgang Schmidt. Those are important questions in number theory, but what they proved, oops, I don't know what happened here, something happened here. What they proved is that this intersection is not more than, well, not n to the 4/3 what we had, but n to the beta, where this beta is smaller or equal than 3/5. Well, I should say plus epsilon, but so this is better than what we had, 2/3. And of course larger than 1/2, because still Pavel's construction, the parabola works here. And this is the conjecture that the truth is here. And it seems that very hard to prove. There are proofs for even if you know that your curve is even more smooth, but two other big names in number theory who proved the conjecture, that was Bombieri and Pila. So they proved the smaller or equal 1/2 plus epsilon for, or something like that, for F infinitely smooth. So that's C infinity. Good. So what I wanted to say here is that I think that, well, reading those papers, these are moderately combinatorial. So maybe we have a chance, maybe using, like here, they didn't know crossing number and they didn't have that proof. Maybe here we can include a little bit of smart combinatorics and discrete geometry to get an improvement. The big thing is this, 3/5 exponent. To improve it, or even to find a simple proof for this. That would be also fantastic. Good, but still, let's go back to the unit distances problem. How much time did I use? Okay, about 20 minutes. So there is another annoying, not counterexample, but example which shows that something is going on. So we understood so far that if we don't focus on really on the unit circle, Euclidean circle, then we are in trouble. There are constructions which would give you quite a few unit distances. Now, before I go any much further, what I wanted to say is that in this sense, there is a very nice result of Jirka, who proved that, I write that most norms have almost linearly many unit distances. And almost linearly, let's be more specific, not more than log n if you have n points. So un for these special norms, I just add here this convex looking thingy times log n. So I won't make it precise what bare category means, but it's something like most of the graphs have certain properties, like the random graphs, which are not that easy to find. So unlike our examples what we had before, this Jarnik and Pavel's construction, and there is a family of similar curves one can deal with. I won't go into the details there. Those are very, very exceptional things. And even the circle itself is special because we see that there the number of unit distances is more than log n over log log n. But this is, as I started to say, this is like with random graphs. We know that most of random graphs have certain properties, but actually to come up with one is hard. And here it's an open question that actually find a norm with where you know most of them have this property with I don't know, say, what did I say here? UN n log n. You can always find n of them. Log n log n squared. I'm just saying, so something less than what you have with the unit circle. So here we have with the unit circle that we want to show, or we know that most of the norms have much less unit distances, but we can't come up with any. So there is this other direction of the unit distances problem, which seems to be very hard to deal with. So this is a question. It might not be as hard as with the case with random graphs. With random graphs, that's a whole industry to try to come up with a construction which carries some of the properties of random graphs, like the Ramsey property. Here maybe you can come up with a construction. I have a conjecture that okay, but let's not talk about it. Let's stay here now. Why is this log n? So this log n is there. You can't really avoid this log n thingy. It doesn't matter what is your norm. If you build one construction with n points with quite a few unit distances, then you can always have a copy of that. Just choose any direction in this direction and translate your whole set in this direction with unit distance. So you had n points, now you have n new points, and you know you have all the unit distances what you had before, and also the same thing in the new copy, but you have the extra n unit distances in this way. And we didn't use any property of the norm. It works for any norm. So from here you have that UN for any norm is always larger or equal than some c times n log n. Okay. Good. So I promise that there is one more. I will show you one more annoying example, and that will also bring another open question. This was actually a very old conjecture of Leo Moser, that he thought that if we have a sphere in 3 space, so we are in R3 now, but this is a sphere. It's not the nicest drawing, but anyways, then the number of unit distances here on a sphere among n points is always smaller or equal than some c times n, constant times n. then so he overlooked something, and you know what did he overlook, but some of you know that. So that was pointed out by in a paper by Erdős, Pickerson, and Pach, and Jani Pach, that not quite. If you see just the special, so if this is the unit sphere, so with radius 1, then if there is a nice construction where if your unit distance is unit distance, if the distance where you are trying to count the number of occurrences is √2, then you can easily find again n to the 4/3 unit distances. That's a nice construction. I won't even explain it now. It has something to do with point line incidences. You simply have an arrangement of points and lines with so endpoints and lines, points, lines, and the number of incidences for every line you have about n to the 1/3 points incident, and then you put a sphere on top of it, and every line with the center of the sphere will cut you a main circle, and there you have many points stepped by those points, and those points with the North Pole and the South Pole will give you this distance, and from every point you have then n to the 1/3. So this is another case when n to the 4/3 is sharp, but still the conjecture, which I don't know what to think about, that if your distance is not √2, then the number of pairs where you see this distance d is smaller or equal than some constant times n. Maybe there is a smart construction, but you know it's very hard to find a construction on a sphere, but maybe there are some other nice constructions to use. So, okay, so those were the obstacles, why we can't do anything, or it's very hard to improve this bound to go any further than n to the 4/3. Now let's see the promising distances, or promising results, where maybe one can go further and one can do something. And as I said, both of them will go into algebra. One is to advanced linear algebra, and the other one will go to algebraic geometry. But the tools I'm using or I'm referring to are relatively simple to state. We don't have to go into the proofs. We can simply just use them. Okay, so the ways to attack, if there is a way. So that was the first result was by Peter Brass, who said that if you have only k directions, so you fix this k directions, and then u in this k direction n is I don't remember what was his result, but I think I write here now, I think it was c times n, but I write here 1 plus epsilon to be on a safe side. This is a true statement. Yeah, maybe this one, or maybe as k goes then. So for fixed number of directions, and that's good, but this can be generalized. And there are two papers.
I'm sorry, but if you have k directions, then isn't the degree of every point just 2k at most or something?
Yeah, I'm confused now a little. It seems that this is like a trivial result. So Probably this was a much nicer dependence of K. So K grows and still, so K grows and still the number of directions is linear. But I have to check. So I also have to admit that I never seen this paper. I just saw references for that. So what I know is what I did with my students. So that was with Schwartz, with Ryan. What's going on? That's me and Frank. And what they or what we did is that if the let's see the first one, that if the angles here are rational multipliers of pi, so we only count unit distances where the angles here are rational. This follows from a theorem called Mann's theorem. Implies that n with angle rational is smaller or equal than n to the 1 plus epsilon. And we went further, and here is a beautiful result from number theory. Actually, it comes originally from Diophantine approximation, and it was first stated by Wolfgang Schmidt, the same Schmidt who I mentioned already. Subspace theorem. I'm going to use a variant of that. So this was the, let me state first what was Wolfgang Schmidt's first result. This one, what I'm going to say is a generalization of that. But it says that if you have, if gamma is a multiplicative, is a subgroup of complex numbers, and this gamma is the rank of this gamma is bounded, is smaller or equal than a bound. What does it mean? So there are, say, B elements which will generate it. So say you have generator 1, generator 2, and up to generator R. And gamma will be all the elements which are generated by them, the product, inverse, and other things. Okay. Is it clear what is bounded rank means for? So it means that a few elements will generate it. So gamma is here. And then you have two arbitrary numbers, A and B, complex numbers, say not zero. And you have the very complicated equation A times X plus B times Y equals 1. And you are interested about the number of solutions. So the number of solutions. Now, of course, the number of solutions of this one, choose your X, I will choose the Y, and there's a solution. But there was this gamma, number of solutions where X and Y are from gamma is smaller or equal than some uniform bound depending on B only. You understand the statement, yes? This is a beautiful statement. It's hard to prove, but it's very useful. And I'm sure, or I hope that many of you are going to use that. So if you don't know this result yet, then let me just show you the beauty of this result. So, okay, let me show you. Maybe you don't mind. And then I will show you how is it related to unit distances. But I'm going to ask you now, of course, it's a known question, but prove that if you see the powers of 5 and the powers of 7, say, then as they grow, the gap between them is larger and larger and larger and larger. Do you understand the question? Well, I know it's a Zoom lecture and usually we don't ask audience in questions like that, but there are many ways to prove it. So what I'm saying is that you have two powers of, well, A and B are integer and they are growing. And what I'm saying is that they will never, I mean, they might be close to each other at one point, but after that, they will never be close to each other. The gap between them is larger and larger and larger. And you won't see the same gap more than constant time. So it's larger and larger. You might see such questions in Kömör, that's the Hungarian mathematical journal for high school students, because there are ad hoc methods to solve it. But how would you use this theorem here to solve? Any suggestion maybe from the audience? Maybe not. So what we can see the group generated by 5 and 7. That's a group here as in the theorem. And what I'm interested about, that how many times can we have some 5 to the x minus 7 to the y equals a d for one distance. How many times can we see this distance? And well, this is the same almost, because you can divide it by d and you can say it's 1 over d times 5 to the x minus 1 over d times 7 to the y equals 1. And we know that for any d, the number of such solutions is smaller than of xy, because they are from this group. Yes, you take the power is of such xy is smaller or equal than this ub. Okay. This was just one way to remember to the simplest form of the subspace theorem. But now I'm going to state actually the subspace theorem. As I said, this is a really powerful tool. We used it in combinatorics. So if you are interested, and I hope that you will find it interesting, then please refer. I wrote a survey paper with Ryan. Actually, we wrote it because Jarek Neshetril told us to do so after a in Pisa. He said that, oh, we should write this survey, and we decided or agreed. What can you say if Jarek says something? And I think that the title is Combinatorial Applications of the Subspace Theorem. Very good. Right, so the theorem I'm going to state is due to Evertse, Schlickery, and Schmidt. And this is the same thing. So gamma is still, we have the rank, so I don't have to state it again. The only difference is that now we have a larger system. So we have A1 times x1 plus a2 times x2 plus up to an times xn equals 1. And we are searching for the number of solutions of this beautiful equation. So AIs are arbitrary numbers from, for us, it's from complex. They state it for other closed fields also, but let's not worry about it. And a number of x1, xn solutions where these are from gamma. And there is another condition which is necessary, because here you might have, say, +1 and -1, and then they would, you can write any number here, everything else is 0, and the same number here. So you have infinitely many solutions. So what we are looking for are the non-trivial solutions, or that's where the name comes from, subspace theorem. The solutions can be covered by those solutions where it adds to 0 by finitely many subspaces, but let's not worry about that. Let's just say that under those conditions, the solutions, doesn't matter. The solutions, the number of solutions which come from gamma with so here is the avoid the trivial solutions with no subsums on the left vanishing. Is at most. So this will depend now the uniform bound, which will depend on the rank bound, of course, but also on n now. But this is still a constant, and it has some quantitative bounds. Maybe I can say that if we see the most recent bound, then it's about, just to see the magnitude, it's about 8 to the n over 4n cubed r and a little bit here. Right, so this is not that terrible, and the time is running pretty fast. So let me show you how to use this for the unit distance problem. And here you have to use the fact that we are talking about the Euclidean circle. So this is in the direction which might help. And of course, if you have these 2 points at unit distance, then you know that this is actually a complex number of unit norm. So you can represent this difference here with a complex number, and we know that the norm is 1. And I don't know what happened here. It says that I should so don't change. My tablet is playing games. So anyways, we can consider them as complex numbers of norm 1. And at the same time, when we proved this result with my students, also Jirka had this his paper on this bare category, that most of the norms have very few unit distances. And he also used the fact that if you have many unit distances, then you definitely have many circles, cycles in the graph of this unit distance. And this gives you an additive property. If you take the sum of those, so if this is Z1, Z2, and so on up to Zk, okay, then sum of Zi is 0. So here is the linear relation, and this is almost like what we need here, right? If we move at least, say, Z1 to the other side, Z1, but any of them, Zi, and then you have I goes from 2 to K, Zi. This is still not 1, but you divide everything on the left with this one and you have 1. So then it follows that if you know that your unit distances come from a multiplicative group. So now those are on the circle. This is the complex unit circle. If you know that those entries come from a multiplicative group, then you can apply that the number of sums is bounded, and what is left is a little bit of graph theory to count the number of circles, cycles, and you know that if your graph has many edges, then it has many cycles, so you get the contradiction. So this is the point where real algebraic geometry, actually it's not real, it's abstract, but where heavy algebraic geometry comes in the picture. And you can check that Erdős construction, the original one, when you had the grid, the integer grid, then we proved it in the paper, then those unit distances actually form a low rank subgroup. So using the bound, you can prove that if your directions, what you are considering, and you only consider unit distances with that angles, then those are from a multiplicative group of low rank, then you are safe. So what is left is that one should really find a stronger arithmetic structure here. And I'm almost up, my time is almost up, so one more step. This is all can be found in a paper. There is another one, which, so another technique and tool, which I don't really have time to talk about. This is with Zev Dvir, Garg, and Oliveira. We had a result. So, you know, if you know polynomial partitioning is one of the main tools in discrete geometry. And if you analyze those constructions, when the n to the 4th third is sharp, that means that you will find some small windows of this arrangement when you have, say, m points. M is much smaller than n, but not, well, actually, it's a polynomial. M points. And some constant times m squared arcs, unit circle arcs, unit circle arcs, with which have with at least 3 points on it. And probably it's not possible. That's another problem of Erdős. Among n points, what is the maximum number of unit circles which contain at least 3 points out of it? And if you can prove that, what is the maximum number of unit circles containing at least 3 points? And nobody knows. So, of course, if one can prove that this is little n cubed, n squared, sorry, then this would go back and break the n to the 4th third bound. And this also implies that if you change the unit circle into Powell's parabolas, then you can't. There are c times m squared of that. here, the best result is due to Elekes, Gyuri Elekes, who find a construction with n to the 3/2 such circles. Well, he didn't know, but there is an earlier result, and this is the last one I show you because it's, yeah, the time is up. That there is a classical geometry result. It's Johnson circles. And this is a very nice, elegant statement. If you have unit circles, 3 unit circles, my drawing is not that nice, and you see the 3 intersection points, then they form another unit circle. So that's another unit circle. So if you have like k circles, k circles containing the same point, then they will give you k choose 2 intersection points, and they will all, well, for all triple, you will find an arc, and that will give you actually the same bound. But this was not known to Gyuri. So the open problem here is to show that this is not possible. And the work which I won't have time to explain with Zevdvir and Garg and Oliveira, we proved that if you had C times n squared co-unit circular triples, then you could choose some constant which depends only on C points that if you stab them, if you fix them, then the whole system is rigid. Now, one would expect that if you can arrange C times n squared endpoints that contain C times n squared such triples, then it contains a rigid part. But rigidity, the theory of rigidity is not quite there. We don't know how to do that. That would also break the n to the 4th third bound. And at that point, I think I stop. There are so many other things to talk about, but this time is up. So thank you very much for your attention.
So thank you a lot, Joshi. And if people wish, I would ask them to join me in thanking Joshi with an applause.
Yeah.
So are there any questions? Just go ahead if you have any.
Can I have a question?
Sure.
So can you roll back to Erdős, Hickerson, Pach, please?
This one, Moser, or?
Yes, yes. So I think that you didn't mention that this is known to be false for every D. So in the Erdős, Hickerson, Pach paper, they give a construction that has n times log star n unit distances for every sphere.
I see. No, I didn't mention that. Here you have n to the 4th third.
Yes, yes. For d equals square root 2, you have that. And for other Ds, they give n times log star n.
Even for 3D? On the 3-dimensional sphere, you mean?
For the spheres, yeah. For every sphere, they do n times log star n. And in fact, I think Pavel was here. So Pavel and Konrad have a paper where they improved that to n times square root log n unit distances.
No, I didn't know that.
So in every sphere, you can have many. I mean, I also didn't know. I conjectured this independently of Moser, and then Géza and János told me about this.
I see. I conjectured that it can't be linear, but apparently it's too late to conjecture something which was done by others. But thank you very much for the information. You think it's in the Erdős, Ickerson, Bach paper already?
Yes, that n times log star n, it's a very nice construction. I mean, you should read it.
Because I kind of recall hearing it from Janos that it should be linear. Yeah, okay, it happens. I will check that, and thank you very much for this info.
And I would also have a question for, if you scroll, oh, okay, just a little higher. So for general norms, is it possible that n times log n is the best bound?
I would think so. I think this log is a technical issue when you have larger and larger circles. So from the proof which I did show you that there are sums which add up to 0, you can imagine that for certain norms, this would be an accident. So for most of the norms, this would be an accident that you go down, and you come back for many circles. And yeah, so but Jirka used more advanced tools from an earlier paper of him and I think his students. I don't know. Yes, so here I expect that this log n might be eliminated. And also when we talk about rigidity and this n log n, then let me mention that if you see the cube, yes, there you have it's a three-dimensional thing, but when you push it down, you think of the edges as bars and the vertices as joints. So you can push it down to the square and they are wiggled, so that's very not rigid. But so this has something to do with this. But one would think that if you add a few edges, then any unit bar system had at least a rigid part. So that's also this n log n times something that would make things much more rigid.